Hello guys, I'm back. My name is Jefferson. I'm a chemical process engineer with expertise in plant design, and hello guys, I'm back. My name is Jefferson Costa. I'm a chemical process engineer with expertise in plant design, and I will start the live session in some minutes. I just need to share the link to this live session in my Telegram channel, in my LinkedIn, and also in the Facebook. And until I do that, please let me know where are you from. I always like to know where are you from. Usually I have people from India, I have people from Brazil, and people from Middle East, and it's very, very nice to know where are you from. And you can see, if you already follow me in the live sessions in the social media, I'm not at my home right now. I am at the hotel because I'm doing some field activities. In fact, this live session was supposed to be at 8:30 p.m. here in Brazil, but I stayed at the field in the industrial facility up to 8 p.m. and after that I left the plant, and I bought a pizza, and I talked a little bit with my wife, and as I have promised to do this live session, I'm here today and I'm here now. So let me share the links for other people. So, okay, I already shared the link to the live session in my Facebook, in my LinkedIn, and also in my Telegram channel. And what I will do here is share some my experience with pressure control, and we'll talk a little bit about that, what I'm doing in the field. And this is a little bit different than I'm doing every Saturday, because on every Saturday I have a guest where I talk about a subject related to chemical process engineering plant design. And today I'm here alone, and you can see that I'm still in the suit. I didn't take a shower because it was my commitment to you to not lose this live session, because I left later than I supposed to be left in the industrial plant. So I will try to today I'm only with one screen, and I'm only with my notebook. Usually I have another screen at my right side when I'm doing the live session at home. So let's see how I can start sharing content with you. Okay. I wanna see my okay. So okay. I will follow the chat by my cell phone. Okay. Sorry for this disturbance, but guys, no one told me where are you from, so please interact with me. It is 10 p.m. here in Brazil, and I would appreciate to have some kind of interaction with you, because my chat is not working. Okay, so now I'm with the cell phone, and it will be easy to me to follow what you are talking to me. So I have Everton from Atibaia, São Paulo, Brazil. And Everton, I think this Everton, I'm not so sure if he is my friend, because it is abbreviated here. I have also Josuel Cordova Carlos. Hi guys, here from Lima, Peru. Nice to have you here, Josmel. I spent some months in Lima, Peru. In fact, it was in Callao, starting up a hydrogen plant in Callao for Repsol. So I spent some months there, and Miraflores is very, very beautiful. I have Akshay Patil from India, and thanks a lot, Akshay, for being here. Akshay is one of my students in the Process Booster training program, and my dear friend, chemical engineering guy, is here also. Thanks for giving a hi, Emmanuel. And if you want to know more about Aspen Plus, the chemical engineering guy is the best guy that I know to help you with that. Everton. Thanks, Everton. Everton is a friend of mine. He was one of my guests in a previous webinars that I did online, and it's very nice to have you here with me. So guys, let me starting with what I want to say to you. So what I will discuss with you today is about control loops and pressure control or something like that. So I will talk to you about some general information about that, what kind of information we need, why we do that, and what kind of deliverables is involved. And with that, my plan is that to get more familiar with this kind of control, and let's see how it will go. So the first thing is, let's start with the problem that I have here and what I'm working on here in the field. I spending more than 1 week here in Rio de Janeiro to do the commissioning of a new pipeline to the customer, and there is not much issues about this new pipeline. but we need the team needs to do the tuning of the control valves, and that's depending on the control that the customer is doing at his side. And the big challenge is to integrate that, because once he has a blower at his side, at the battery limit of his, and when the blower load and unload, it affects my plant. So the main issue today, that's why I left so late from the plant. But in general terms, what is this process? I have a blower that gets biogas from the landfill, and this biogas is compressed in order to give the minimum pressure at the compressor that will compress that to around 7 bar G and send to the process plant. And in this process plant, I will remove the CO2, I will remove H2S, and in the end, I will be able to have biomethane ready to fuel trucks to the market. And eventually, when the compressor stops, and there are some events that stops not only the compressor but also the purification plant, and in this unit, I need to release this gas to atmosphere. I need to release this gas. I cannot just shut down the blower and prevent from taking the gas from the landfill, because in the landfill the biomethane is produced by microorganisms, and if the pressure there increases, it affects the efficiency of the landfill. So because of that, if my compressor stops, instead of sending the gas to the compressor, I need to send this gas to the flare. And that's why I have a PV here. Why I have a PV and not a TV or not a FV? So the first thing that you should get familiar is with the nomenclature that we use during in control. So the main source of information to you will be the PNID symbol chart, but we can evaluate and we can predict that PV means pressure valve. And this pressure valve is named pressure valve because it is associated with a PIC, and the PIC in this case is pressure, indication, control. It is my controller. So to have a control loop, I need to have a source of measurement, I need to have a control, and I need to have a final device that will take the action to change or to control the process. So if I didn't have the automatic control, or if I didn't have the control, what I could do is open or close the PV manually. Or in the other hand, in the other case, I could isolate the PV at the downstream and at the upstream and at the downstream, and I could have, and I did this sometimes today in the field, I could open the bypass of the control valve more or less, and this is in these manual actions I would be doing the work of the controller, because what the controller do in fact is automate an action that could be done manually. So instead of having someone to regulate the pressure at the discharge of the blower manually, we have the control that will do these tasks for us. We have Sérgio Manuel Maitá Paucara. I believe that it is Brazil because of the Sérgio Samuel Maita. It seems to be a Brazilian name. And thank you, Emmanuel. Thank you, Sérgio, for being here. And so I will share with you some kinds of pressure measurement. And now that I have a new customer, I need to guarantee the minimum pressure for my compressor, because before having the customer, my only issue was when I stop the compressor, I should release the biogas to the flare, and that how I could do that automatically. When I have minus millibar G at the suction of the blower, it is designed to deliver the biogas at 100 millibar G, and because of the pressure drop in the pipeline, it will reach the compressor around 50 millibar G at 800 normal cubic meter per hour. But when I stop the compressor, I will not taking the gas. So the gas that is in the suction of the blower will be compressed, but as it doesn't have where to go, it will build pressure at the system, and the pressure will increase. And to prevent any kind of damage in the pipeline or in the suction of the compressor, I release this pressure opening the PV. And to do that, I need to define a set point that best fits to my process. And in this case, I set the set point as 120 millibar G. So it means that I run in my process with 100 millibar G, and my compressor is running also. And because of the pressure drop at the pipeline, in the suction of the compressor, I have 40 to 50 millibar G. But once the compressor is stopped, the pressure will build up, and when it reaches 120 millibar G, my PV will start opening. And once it's starting opening, the pressure will be controlled in this set point. If I have too much flow, my pressure will open more. If I have a small flow, my pressure valve will open less. And this is, it is important to you understand what is the kind of action that we have in the control valve, because the controller will send a signal to the control valve, and I need to know if I increase the signal, my valve should increase the opening also, or it should decrease the opening. And there is two kinds of control actions, and the first one is the direct action. It means that if I increase the signal that comes out from the PIC to the actuator of the valve, it should also increases its opening, and I will talk more about that. And in the opposite side, I have the reverse action. And in the reverse action, when I increase the signal of the controller, my valve should close. And this kind of association or this kind of working, it is possible to associate that because we are talking about a fail close valve. And this is another kind of information that you should know about control valves. What is the safe position in a case if I cut off the power supply in the valve? and the power supply could be instrument air, could be electricity, could be something hydraulic or something like that. So when my FC here below the control valve means that if I lose the power to actuate the valve, my valve will go to the closed position. So it means that if it is a valve that has a signal of 4 to 20 milliampere, if I send a signal of 4 milliampere to this valve, it means that it should be zero. It should be closed, zero opening. On the other hand, if my controller sends a signal of 20 milliampere to the controller of the valve, it should be 100% opening. And this is the way that it is. If it was a fail opening valve, it should be the opposite. My 4 milliampere would be 100% opening, and my 20 milliampere should be 0. But Everton knows, and the automation knows, that is possible, although the action of the valve is the opposite because it is a fail opening. There is a mathematical equation that we can do that the valve actuate at the same way. For instance, we could add 1 minus the signal of the controller, and a control valve, fail open control valve, would be actuated like a fail close. Let's it seems to be okay. Let's do an example. And sorry, I don't have anything to write to you. But if the controller sends a signal of 20%, let's think about percentage and not milliampere. If in a fail close valve, if the controller sends 20% to the fail close valve, it will open 20%. If it sends 50%, it will open 50%, and if it sends 100%, the valve will be full open, 100% open. But if we are talking about fail open valve, 20% of the signal means that the valve is 20% closed or 80% open. Why? Because when I have 100%, it is 0 opening, and when I have 0 from the controller, it is 100%. So to prevent this kind of information, to prevent the operator or to prevent the process engineer from thinking that it is a fail open valve, I need to think at the opposite. What the automation guys can do to solve that is 100% minus the output of the PIC. So in this case, the fail open valve will start with 100, and if the information is 0% here, that should be the valve 100% open, it will get 100 minus 100, it will be closed. And this way, when I see the valve 20% opening, it doesn't matter for me if it is a fail close or a fail opening. If I see 20% to the valve, I know that it is 20% opening. And for us that are doing the verification of the system, the process engineer, the operators, what matters for us, in fact, in summary, what matters for us, process engineers and operators, is know the opening of the valve and not the signal that goes to the valve. The signal that goes to the valve is important to the instrumentation guide and to the automation guide, because they can evaluate if the valve is the actuator and the controller is working properly. But once that is finished, is commissioned and ready to run, what we don't care about that. We process engineer and operators don't care about that. What we want to know is the valve is 20% opening, it's 40% opening, 60 and stuff like that, because with this we can associate some process values. When the valve is too much closing, too much open, we can associate something like that. Thank you, Everton. Thank you. So Everton is automation guy, and I should take care to not say something wrong here, because for sure, my friend, please correct me. And in the future, I will invite Everton to talk to me in the live sessions, and there we'll be able to talk more about this kind of stuff, and will be very nice. So Everton, I'm using this live session to invite you to be a guest of my in-process interviews, and I hope you accept my invitation. You don't need to answer right now, but consider that, okay? And I have a relative here also. Alison Cardozo is a relative of mine. So Alison, please, thank you for being with me right now. So guys, what we have seen up to this point is that the controller can be direct action or reverse action, and we have seen that the control valve fail position can be fail close, fail open, but there are other types of fail position, like fail stop or fail and it will closing but not automatically and slowly and something like that. And another important thing that you should know is how to calculate the dcv of the valve. And I received a question related about that today or tomorrow, I'm not so sure, and from a student from my training program. And when we do the process simulation, we need to do the process simulation with the design conditions, and the design conditions can be the average or can be the maximum capacity depending on the purpose of your process simulation. But what matters is that for CV calculation, we should consider the maximum value at operations. So let's suppose that in the average, I will have a flow here of 800 normal cubic meters per hour passing through DPV to the flare. But I know that it's possible that I can have, for instance, 1,200. So I will calculate the CV of this valve based on 1,200 normal cubic meters and not in 800 normal cubic meters. And we'll do that because we need to evaluate the range of operation of our control valves. So depending on the type of the control valve, it will have a best range of operations. And if it is a globe type, it will be one range. If it is a ball type, it will be another range. And if it is a butterfly valve, each kind of valve will have its own characteristics. So what we usually set at the program, and the best way to calculate or to estimate, in fact, a control valve is use the supplier software. For instance, Samsung has its own software, and Heater has its own software, and with that we can predict the size of the control valve. And it is important to predict or to estimate the size of the control valve, because with that, at the preliminary stages of the project, we can the pipe engineer can verify the fittings that must be added to the pipeline. Much often the size of the control valve is smaller than the pipe size. And talking about control, if we are talking about isolation valves, usually it is the same size of the pipeline. So if I calculated a 4 inches pipeline and I did the preliminary sizing of the control valve, I will able to inform the piping engineer that he or she must consider at his arrangement the reductions, and also I can estimate the cost of the valve, because a control valve, a 6 inches control valve, globe 6 inches control valve has a different price than, for instance, 8 inches butterfly valve. It's totally different. So during the basic engineering, we can do this kind of calculation. It's more likely to do that in the basic engineering. And in the detailed engineering can be a revision on that and do the purchase and the delivering to the field. So my tip here, or my information here to you about DCV sizing is: 1, consider the maximum operating flow that you can have, and you will add also the normal flow that is expected, and you will be able to see the graph, and if the points of operation that you expected to have is between the range of control of the valve. And another information that is important here during your CV sizing is about the noise, and the noise is related to the Mach number. And I received today another question related to this subject, and it talked to the question was if the choke condition is good or not, or if it's bad. I think that it was something like this. Is the choke condition at the control valve bad? It's not bad. It is a condition of the process when you have a big differential pressure, and considering that you have a fixed orifice size. When you reach the choked condition, it means that even though you increase the pressure drop, you will not have more flow through the orifice, because it reached the choked conditions. And what is important in the valve is that you prevent having noising, and it is related to the Mach number, because if the Mach numbers and the Mach number is related to the speed of sound, if you have a too big Mach number, you will have very noise, and you will have also vibration in the valve, and that vibration can lead to your control valve broke, and or not control. Not do the kind of control that should be done. And what we can do in this case is increase the orifice of the valve, or change the type of the valve to reduce the Mach number, and with that to reduce the vibration, and with that to reduce the noise of the system. So what we do during the sizing of the control valve is to inform the process conditions and to the supplier, and we can use that in the supply software, and we need to evaluate if the results from that conditions, and of course that conditions includes the fluid, the properties, and the process conditions. In process conditions is flow, pressure, and temperature. All of these will result in a CV calculated, and most often the CV calculated is not the CV that will be installed in the field, because as we have in the related to pipes, we have the same to the control valves. The suppliers do standards control valves, so there is a set of control valves that fits a range of CVs. So you calculated, for instance, a CV 10 for a process, but if you go to the supplier, it only has a CV 12 or CV 15, for instance. And you will need to buy the CV for 12 or 15, of course, evaluating the curve of control. And once you have that, you will have the characteristics of the valve, like the noise and the Mach, how it fits to your process. And that leads to another subject, but before doing that, nice to have you here. Jante Carbozo is also a student of mine in Process Booster. Nice to have you here. And so we talk about a lot of things, guys, and another related to CV, what happens is that depending on your process, the evaluation of the fail opening position of the valve, that can be an issue, especially if we are talking about pressure valves, because pressure valves means that we need to control a delta P of a system, and in this case I'm releasing the pressure to the flare, and we could consider that something like atmosphere. But let's suppose that instead of having the PIT at upstream of the PV, we had the PIT at downstream of the PV. In this case, we want to control the pressure downstream. Most often it happens at much lower pressure than upstream, and in an event that this PV fails, we can overpressurize the downstream of the system. And let's suppose that instead of working with 100 millibar G, I was working with 100 bar G, and downstream of my PV 211, I want to work with 68 bar G. And it is an example that my friend Mohammed Hassan has opened a discussion in LinkedIn, and he would like to know what condition he should consider to do to take the mass of the load to the PSV that he should add in the system. And he had a series of control valves, I think 2 control valves in series or 3 control valves in series, and he had 100% 100 bar at the inlet of the first control valve, and in the end of the process he had a PSV with around 15 bar G, and between the 100 and 15 he was breaking the pressure in order to to get the values that he wanted in the process. So he was discussing how should be calculated the load of the PSV and at 15 bar G, and how should be the schedule of the pipeline in this series. And what I talked to him was that once between the first PV and the last PV we don't have any PSV, he should consider all the system rated to 100 bar G. And why? Because if I open this bypass, for instance, I will not have the control valve limitation. And if my PV is leaking, I will not have the control valve limit. I will have the control valve limitation, but I will not prevent the system from overpressurization. And if for any reason the PID of the controller is not right set, and we'll talk about that, it could open too fast and we could have the overpressurization. So what will prevent your system downstream of a control valve to get to not erupt because overpressurization is or a PSV, and PSV is pressure safety valve, and it can be also a pressure safety device if you want to, and or the material. And if I rate the material to the maximum pressure of the system, there is no problem. But if my material pressure rating is below the maximum is below the maximum available pressure, it is a point to be discussed and evaluated related to process safety. So returning to the pressure controller, to set the PIC, I have three main information. And before doing that, let me show you some examples here. So here I have an example of a pressure indicator. So you can see here that I have the information of pressure, and the information of pressure is millibar G, and I can see a range from minus 60 to 0. So this is a pressure indicator, and this kind of instrument in the PNID will be identified as PI. It's only a PI. However, I can have a pressure indicator transmitter, a PIT. And in this case, you can see that I have a pressure indication. It is minus almost 21 millibar G, but I have cables, and these cables are for transmitting the information to the PLC and also to receive electrical power to allow the working of this device. So we can see also that it is proper to explosive atmosphere, and it is a special kind of enclosure to not have any kind of sparkle and allow some explosion or a sparkle to a flammable gas and something like that. So what matters here is that we have a pressure pressure measurement, but it is also an indicator and it is a transmitter. And this kind of instrument is able to send the signal to the control room. The other one, the PI or the manometer, is only the operator is only able to read the measurement at the field. Here no, we can read the measurement at the field and also in the control room, because the signal goes to the PLC, and if we have a supervisory, it will get the information and something like that. And finally, here I have a PT, and it is a pressure measurement device also. And in this case, I don't have the I, that is the indication. I have only the pressure and the transmitter, and you can see some cables here, and here has the electrical information to the PLC and something like that. So in your PNID, you can see these three kinds of information. It can be a PI, and it can be a PI in the field only, or you can have a virtual PI in the control room. And it will be possible to have the PI in the control room or the screen of the control, the screen operation screen, only if you have a pressure transmitter. And the pressure transmitter can have an indicator in the field, so in this case is a PIT, or it can be only a transmitter, and in this case only the signal goes to the PLC and to the control room. Here is the system that I'm showing you. So we have the isolation valve, we have the bypass valve and the control valve. And in this case, the control valve has a controller, and there is the instrument air going to the control valve, and in this case it is closed, and we have a positioner, and sometimes we don't have this kind of positioner in the control valve, but we have a reference for the opening, and we can see here once the control valve opens, and it is a kind of segment ball valve, it will go to the left or to the right in order to open more the orifice, do the opening of the control valve. Okay guys, so now what I want to show you is I will talk to you about the tuning of the control valve. So what is the tuning of the control valve? The tuning of the control valve is the settings of PID of your controller in order that your valve fits to the process. It controls the pressure of the system based on the variation of the pressure. And an example of PID graph you can see in the thumbnail of this live session. There is a graph with different integration numbers, and depending on that, we open the valve more faster or slower. Depending of the proportional, we open more or we open less. And to evaluate if your PID settings is okay, you need to know about SP, about PV, and about OT. The PV is the set point, it is your target. So in this case, I set my system at 120. So once this valve is opening, I want to reach 120, and I don't want to operate at 130. I don't want to operate at 150. I don't want to operate at 100. I want to get 120. So this is the set point of my controller. However, the real value that the transmitter is reading is shown in the PV, and PV is the present value. It means that the instrument is measuring this value at that time, and based on the set point and based on the present value, the controller will define a signal of output. It will define an output, and that output will be sent to the controller in order that opening more or closing more, the PV will get closer to the set point, because in the end what we want is that the set point be equal to the PV. In fact, we want the PV to be equal to the set point. And if your process is well tuned, and sometimes it is easier, sometimes it's not so easy, you will get that, and the graph of variables you will see will be a straight line if your process is stable, or it will be a solenoid line, because if it is not so stable, or if your tuning is not doing so good. So based on that, this photo is not so good, sorry. It was a sunny day, and there are windows behind the control, the screen, so sorry for that. But what we can see here at first is that we have in this case we have options to have the controller at the manual or at automatic. And if I set the control to manual, it means that to open or to close the control valve, I need to define a value of output. And how it is configured or how it is programmed depends on the philosophy of the company. In this company, for instance, they shift or they separated the OV from the hand value inputs. So in this case here, if I set my control at manual, what will happen is that I will need to define a value at the HV, and HV in this case means hand value, to open or close my valve. For instance, let's suppose that I set for manual and I want to open the control valve at 25%. So I would type 25% at the HV, and my valve would open 25%. Or if I want to change to 65, I would do the same, and something like that. But as it is in auto, the opening will be defined based on the proportional, the integration, and the derivative of the controller. And it has a calculation, and there are methods to do estimates of this value. But to be sincere, as a chemical process engineer work with plant design, I never did any kind of calculation related to PID. What I do is add preliminary information to the control. So in this case, we started with 0.5 at the proportional and with 0.1 to the integral. And I saw the behavior of the control, and I evaluated that for some minutes. Depends on your process. It can be 2 minutes, it can be 10 minutes. So based on the variation in the process, I know if I need to increase more or if I need to decrease more the information of proportional integration. And most often you will need to work with these two with these two values in parallel. If you have a stable process with your P and I already set it, and for instance there are a disturbance, you increase the plant capacity and you don't have the same kind of control, it is not smooth. To adjust the process, the controller, again, you will need not only change the proportional but also the integral, because they are related one with another. And what I can say about this is that the proportional is how big is the steps related to the opening your control valve. And of course, guys, I'm telling you here what I see in the practice. I'm not trying to be scientifically or use terms of the bibliography. I want to show you the understanding that I get from the field. So I think it's much easier to understand and also much useful. Of course, if you need to do a test or a test for there is a test in India, I forget the GPA. There is a test. If you need to do a test, you should study, because in tests they want to know the right answer, or not the right answer, but the expected answer. So it's not what I'm doing here. What I'm doing here is explaining to you how it works. So the proportional will open more or less your valve, and the integration will define how many times that will be done by time. So if I have a P, a proportional too big, it means that every time that my valve opens or closes, for instance, if my P is 0.5, it will open, for instance, 5%. But if I add a proportional of 2, instead of opening 5%, it will open 15% each time that it needs to do actuation. So what is expected is that with high proportional, your valve will do big steps, and with low proportional, it will do small steps. So this is it. The integral will define how many steps will be done in a period of time. So if I decrease the integral, I will do, if I decrease the integral, I will do less. Everton, are you still there? This sometimes is confusing, but if I increase the integral, I will do more actions in a period of time, or I will do less actions in a period of time. And this is important because if you have a curve like this, you need to change the proportional and the integral in order that it will opening up to you have your process something like that. So what we can see here is it is not so good because there is no much. Nice, Everton, please just confirm to me, if I increase the integral, I will have more actions or less actions per time, right? While I wait for the Everton's answer, you can see it is the graph of set point. So I had a set point and I increased a set point, and it is my present value, and it is my opening of my valve. And it here is not so good to see because I don't have too much variation, but let me see if I have another picture to show you. I have, let me try to find. I have a video here that I did in another project. Let me see if I am able to show you. So here, here I have another graph of controlling, and what nice. And nice. What Everton is saying, that if we increase the integral action, the controller will respond faster, so it will do more actions per time. But it depends of the calculation, and I have seen that in another commissioning, and because the Everton is saying that it depends on how is the equation. Depending on the kind of the equation, normally we have the frequency, but if it's written differently, when we increase the integral, we can be decreasing the response. So it is something that we need to discuss with the automation guys during the commissioning. But if you don't have an automation guy to talk to you during your plant operation or something like that, what you can do is to define small steps, and you do a small step increasing and verify, or you do a small step decreasing and you verify, and you will understand if you increase the integral, if it will respond faster or not, or if you decrease it, if it will respond faster or not. That is the safer way to do that if you don't have the support of the automations, because the automation guys can link the computer at the system and he can verify this kind of issues, and usually we process engineers and operators are not able to do that. So this is my tip, and here you can see another process, and in this process the OT of my system is the yellow line, is this line here at the that is touching the red line. This is a heater, and this heater is responsible to heating up the water system of my process. And you can see that we have 3 lines here, and here what's happening is that the temperature is decreasing, and when it gets a determined value, the heater is starting heating up in order to prevent the temperature to decrease more and more, and it gets a peak, or it gets a highest value, and so it returns in order that I have the modulation of the system. And for me in this case it is very, very good, and I could also work more in this process in order to have a more smoothly, a more straight line. But sometimes you don't need to worry about that. You need to make sure that the minimum values that you're getting and the maximum value that you're getting is at the range of the operations. And if it is at the range of the operations, okay, great. If it's not at the range, we need to set up the tuning. And thanks a lot, Everton. And with that, guys, I need to know if you have any question that I can help to clarify. I don't know how long I've been talking. It seems that I've been talking 1 hour, and I'm still with my suit, so I need to take some bath. So if you have any question, please just let me know. And thanks a lot for the guys that were following me right up to this point, because I know that it is not a easy subject, and I don't have too much resources to share with you. It's more talking and a way that I have to share with you my experience without doing a classic teaching. It's not my way of teaching people. I'm not a teacher, although I'm working more to prepare myself better to do classes. I'm not a teacher, and I try to share with you what I know from the field and from my experience, and this kind of live session is to do that. So guys, I'm very, very tired for sure. So my dinner was this. I'm not so sure if I have talked to you. The pizza and a citrus. If you don't have any question, I'm going. Let me know if you are still there. Thank you, Josmel. You are supposed to do the tuning of your process during the commissioning, because what we do at the first time, we what is the sequence, right? We do the process simulation, and based on the problem that we have, we do the process simulation. And once we do the process simulation, we have the process conditions to define our control valve. We develop or we fill a process data sheet or a specification data sheet, and with that data sheet we are able to do the preliminary sizing or preliminary selection of the control valve. Once we do that and the project proceeds, we do the quotation, and the procurement team buy the control valve. It is sent to the field for installation, and it is during the construction phase of the project. And once it is installed and with all the connections ready, like electricity, instrument air, and something like that, everything it's okay, it's time for commissioning. And the commissioning starts with defining or verifying if the fail-safe conditions of the valve it was mounted correctly, because depending on how you connect the air supply to the valve, you can change the fail position of the valve depends on the supplier of the valve and something like that. So, and once you verify that, the instrumentation guy, and with the support with the automation guy and with the process, in many cases we verify the 0, the 20%, 25%, the 50%, 75% and 100% of the valve. So we send an electrical signal that represents these openings, and we verify at the field if the valve is opening correctly and closing correctly based on that. And we verify not only the field, but we also go to the control room and verify if the 25% opening in the control room is 25% opening in the field or something like that. It is the commissioning, because the valve is already installed. Okay, so we are doing tests before doing the startup of the plant. So commissioning is it, doing verification before the startup of the plant. And once we start and before starting the plant, we add preliminaries values to the PID of the in the controller, and we are not sure what will happen, because to see the valve actuating, we need to have flow through it. If the valve stops, we are not able to evaluate the PID of the control, unless that there are software that are able to do that. I never worked with softwares, okay? So I cannot say if that is possible. Eventually, with my live session with Everton, we will know that. So when we start the plant, and let's talk about the controller, pressure controller that we are talking here, I will evaluate if the operating pressure is at the range that I want to. And I set my controller to 120, and at least my average present value should be 120. But I don't want too much variation. I don't want a solenoid. I don't want I cannot use it. I don't want a solenoid. I want a straight line. And to have this straight line, I will adjust the proportional, I will adjust the integral, and in some cases not pressure, because we use derivative when you have a slow response in your system. So in many cases we just need the pressure proportional indication. We'll adjust that until we have a smooth graph of variables and open. Not the actuation of the valve is not so important as the present value. So what matters for us is the present value, and once we have that, we can and it is during the startup, because I'm not able to do that if I don't have gas passing through. And in many cases, we will not pass a gas only to do the tuning. You will do during the startup of the plant. And most cases, we start with low capacity or downsizing. And it's not downsize that I forgot the term that we use. But we start with low capacity, and we starting doing the tuning of the controllers. And once we increase the capacity of the plant, sometimes we need to change that until we have 100 capacity, and we set the tunings. And if we have too much variation, the tuning should be able to support that kind of variation, something like that. So the tuning, in my point of view, is not is an activity that begins in the commissioning, but it extends to the startup of the system, because without the startup we are not able to finish that. Okay. And eventually, if you are already in a plant that is running, if you change one condition, it is possible that you need to change your tuning again. For instance, you run with one pump, and now you are running with two pumps in parallel, so the system behavior changes. You need to set your tunings again. Thanks a lot for your question, and thanks a lot for being with me up to the beginning. And is it by hand or software? Yes, Akshay. All this is chemical process engineer, and as you already know, I worked not only in the office but also in the commissioning, the startup. While I always did that by hand. I know that there are softwares that do this kind of calculation. I don't know how expensive it is, but I believe that I do that by hand. Okay, so I have worked with small plants and with average plants. I never worked with petrochemical plants. So and as the size of the plant increases, of course, that the money available to do commissioning, to do the startup increases. So eventually, in these big projects, you will have capital to buy automation about this. But I always did this by hand, and I know that there are algorithm and the air separation units has this kind of nice. Let me read here for people. And Everton is helping us. There is software to PID auto-tuning. In general, these softwares are expensive, and I prefer to calculate the PID parameters. You have to define the first order dynamic model to calculate the parameters. So this is the way that he does. For process like this, a first order dynamic model plus depth time fits very good to a real dynamic response. And once you get familiar with more and more process, you understand what kind of first values is can be guessed, and Everton works specifically with automation, so he is much more familiar with the calculations and stuff like that. I never worried about this kind of calculation, and I do by observation, and in fact for me it is the funniest part of the job, because I can change values, I can evaluate the system, and I can do correlations. I see that this valve, see if this valve open too fast, I can see the interaction or the impact that it has in other values or other process values. So this is important to the process engineer to understand what is the relationship between one variable and another. If I increase the pressure, what happens with the purity of my gas, or if I decrease the temperature, what happens with the pressure, and something like that. So this is I like to do this part of the job. Is very nice, and this is only possible if we go to the field, or if you work in an industrial plant. We are not able to do that when we are at the office. So guys, thanks for your interaction, and thanks a lot, Everton. We deserve to do a live session to talk specific about tuning of controls, and I hope that we can do that soon, very, very soon. And when I say soon, is in October, next month. In November. In November, I will have a set of schedules open, and it will be very nice. And thanks a lot, my friend. Thanks a lot for the audience. Thanks a lot for supporting me, not only in the LinkedIn, but also in my social medias like YouTube. And I will do my best to return to you in the next Wednesday with another subject to us talking about, and you get more and more familiar with plan design, not only get familiar with the rules and activities of a chemical process engineer in plan design. And I don't like endings, I don't like to do, but this is it. See you soon, my friends. Up to Saturday. Saturday I will return with an in-process interview with Michael, and Michael is from USA, and we'll talk about process safety. Bye bye.